Welcome back to another exciting day of Algebra 2. Today we are talking about inverse functions, but in order to understand inverse functions, we need to refresh our knowledge on compositions of functions. So we're just going to do a couple quick warm-up problems to review that. F of g of negative 3. So that means the first thing I need to find is g of negative 3. Well, if I plug in negative 3 to my g function, that's going to be 3 times negative 3, which is negative 9. So now what I'm looking for is f of negative 9, which if I plug negative 9 into my f function, that's going to be 2 times negative 9 minus 1. That's negative 18 minus 1, which is negative 19. All right, on to b. F of h of 7. I need to find h of 7. That's going to be 7 squared plus 1. 49 plus 1 is 50, so now I'm looking for f of 50, which is going to be 2 times 50 minus 1. So 100 minus 1 is 99. F of g of h of 2. Wow, that's a lot to get through, so let's work from the inside out. First, h of 2. H of 2, that is going to be 2 squared plus 1, which is 5, which means I'm now looking for g of 5, which is going to be 3 times 5, which is 15. So I'm looking for, lastly, f of 15, which is going to be 2 times 15 minus 1. 30 minus 1 is 29. H of g of f of 5, another working from the inside out. Let's find f of 5. 2 times 5 minus 1, that's going to be 9, which means I'm now looking for g of 9. That's going to be 3 times 9, which is 27, which means I'm lastly looking for h of 27. That's going to be 27 squared plus 1. 27 squared is 729, and if I add 1 to that, I get 730. Okay, so that's all numeric. The highlight of knowledge we really need for these inverse functions is composition of the entire function. So that open circle, remember, means composition. So I'm looking for h of f of x, which means I'm going to be plugging in my entire function of f into my x value into my h function. So that's going to look like 2x minus 1 squared plus 1. Now when you're squaring a binomial, remember you're foiling, so that's going to get me 4x squared minus 4x plus 1, and I still have that plus 1 on the outside, so I can combine those terms, and I get 4x squared minus 4x plus 2. All right, so this is the information we need to be able to do in order to work with inverse functions. So the definition of an inverse function: if I have two functions, f and g, if I take the composition f of g and I get x, and I take the composition g of f and also get x, that means g is the inverse of f, and we notate f to the negative 1. That is our notation for an inverse function. So to confirm if functions are inverses, you have to see if they undo each other. So you take the composition both ways, and you have to get x as the result. So let's practice that. Let's determine a couple times if g and f are inverses. So here's f and here's g. First, I'm going to take f of g, meaning I'm going to plug in g to my f function. So that's going to be 1 minus 2 times 1 minus x over 2. Now, when I am multiplying that 2 and the 2 in the denominator, that's going to cancel. So I'm left with 1 minus x, and I'm leaving it in parentheses because I have to distribute that negative 1. I don't want to forget to do that. So I end up with 1 minus 1 plus x. The 1's cancel, and I'm just left with x. So I'm halfway there. That one gives me x, but I have to verify it the other way around also. I have to find g of f and see if that gets me x as well. So this time, I'm going to be plugging my entire f function into x in our g function. So that's going to be 1 minus 2x over 2. Again, I'm putting it in parentheses because I need to distribute that negative. 1 minus 1 plus 2x over 2. The 1's cancel. I'm left with 2x over 2, which reduces to x. So both ways I got x as a result, which means these are in fact inverses of each other. Okay? Let's look at another problem. B. 2 more functions. Let's see if they're inverses. Let's first find f of g, which means I'm going to be plugging in g to my f function. So that's going to be 1/4 times 12 plus 4x minus 3. Again, I'm putting it in parentheses so that I remember to distribute. That's going to get me 3 plus x minus 3. The 3's cancel, and I'm left with x. But I'm not done there. I got to take it the other way. G of f, which means I'm going to be plugging in f to x in our g function. So that's going to be 12 plus 4 times 1/4 x minus 3. Again, in parentheses because I got to distribute that 4. So that's going to leave me with x minus 12. The 12 cancel, and I'm just left with x. So both ways I ended up with x, so these are inverses of each other. Last one for this example, C. Let's find f of g. So I'm going to plug this entire thing into x. So 3 times 1/3 x plus 2 minus 2. When I distribute that 3, I'm going to get x plus 6. Bring down that minus 2, and I end up with x plus 4. This does not equal x, so I already know that these are not inverses. Okay. So that is how we confirm if two functions are inverses of each other or not. But how do I find the inverse if I'm just given the function? Well, we do so by following these steps. First, if we have function notation, we're going to change it to y equals. Then we're going to swap our x's and y's. Then we use algebra to rewrite our equation to solve for y. We're getting it by itself. And then once we have finished doing that, we're going to put it back in function notation for that inverse, f to the negative 1 power. And then you can verify that they're inverses by doing the composition both ways that we just practiced. So let's take a look at A. I've got f of x equals 5x minus 7. So the first thing I'm going to do, put that in y equals notation. Now to find my inverse, I'm going to swap my x with my y. So that's going to be x equals 5y minus 7. Now I want to isolate y. So this is like algebra 1 stuff. X plus 7 equals 5y. Divide by 5. And I find that y equals x plus 7 over 5. And then lastly, putting that in function notation, my inverse is x plus 7 over 5. Let's practice again. I'm going to change that to y equals 3x cubed. Then I'm going to swap my x and my y. I got to divide by 3. And then to undo a cube, you take the cube root of both sides. And so we find that y equals the cube root of x over 3. And so in that function notation, f to the negative 1 is the cube root of x over 3. That is my inverse. All right, last one, C. This is already written in y equals for us, so we can go straight to step 2, which is replacing our x's and our y's. Now to undo a square root, I have to take the square root of both sides, which means y is going to be the positive or negative square root of x. Now, I can't have two inverses, so this one does not have an inverse. Now, how could we know that ahead of time? I'm going to skip ahead on the next page to where we're talking about the horizontal line test. We're going to go back to example 4 in the graphing in a moment, but let's talk about the horizontal line test. Remember, our vertical line test, the vertical line test, told us if we had a function, determines if our graph is a function or a relation. The horizontal line test tells me if my function has an inverse, meaning that it's 1-to-1. So let's look at A. If I typed this into a graphing calculator or Desmos, what this is going to look like is my quadratic parent function just shifted down 2. So it's a parabola. Okay. If I draw a horizontal line through my graph, it's going to touch 2 times, which means it fails the horizontal line test and therefore does not have an inverse. Okay, so when we had that function previously, y equals x squared, remember that's my quadratic parent function. That's also going to fail our vertical line test, so it does not have an inverse. Let's look at B. This is our rational parent function, and it's being shifted to the left for, we're going to learn more about transformations later. So what that's going to look like, it's actually being shifted to the left 3, not 4, I apologize. What it's going to look like is our rational parent function just moved over. And if I draw a horizontal line through this graph, it's only going to touch once. So it passes the horizontal line test, and it does have an inverse. Okay, so our vertical line test tells us if we have a function. The horizontal line test tells us if we have an inverse. Okay, so let's go back up to the last part of our notes, the graphing inverse functions. So when we're graphing our inverse, we're reflecting over the line y equals x, which is our linear parent function, and then the coordinates of each ordered pair are switched. So if I wanted to sketch the graph of this function and its inverse, all I need to do is make a table of values for my first function, f of x. Let's make an xy table. If I input 0 here, that's 2 times 0 is 0, minus 3, that gets me 0, negative 3. If I input 1, my output is negative 1. If I input 2, my output is 1. And if I input 3, my output is 3. So there I've got a couple good values here, and I can go ahead and plot that on my graph. 0, negative 3, 1, negative 1, 2, 1, and 3, 3. So just connecting those dots, I'm going to graph forever and ever. Okay, cool. Now, for my inverse, all I'm going to do is swap my x and y values. So instead of 0, negative 3, I'm going to have negative 3, 0, negative 1, 1, 1, 2, and this one stays 3, 3. So I'm going to plot that one. And so there are my two functions, my original and my inverse. And what I can do is if I plot that linear parent function, x is equal to y, you should be able to clearly see that it has been reflected across that line. And that is how we graph inverses. So again, we're using our prior knowledge of compositions to verify if we have inverses, and then we're following those prior steps to find an inverse. Horizontal line test tells us if we have an inverse, and then this is how we swap x and y values to graph our original and inverse function.